Welcome to today's SwiftUI tutorial. In this video, we'll enhance this custom daily calendar view by implementing dynamic time components. We'll explore how to transform static elements into interactive, real-time components that respond to user input and system time changes. Currently, when users tap any day in our week view, the task list view always displays today, November 19th, 2024. We'll fix this by implementing proper date handling. First, we'll modify the task list view struct and add a selected date property to accept a dynamic date as a parameter. This allows the parent view to pass the currently selected date into task list view. Update the text displaying the date to use selected date dynamically. Use the formatted method to properly display the date in a readable format. In calendar view, where task list view is instantiated, pass the selected date state variable as a parameter to task list view. While doing this, we'll also fix a variable name typo in both the task list view and week view initializers. With these changes, the task list view will dynamically update its displayed date based on the user's selection in the week view. When a user taps a day cell, the selected date state is updated, and task list view reflects the new date automatically. To display the date in a user-friendly format, we'll use Swift's powerful date formatting. This formatter creates a readable date string like Tuesday, December 17th, 2024. The date components can be customized to match your app's design requirements. Here, weekday gives the name of the day, month gives the month name, day and year include the numerical day and year. Depending on your date's default settings, you can display an abbreviated version or full name version by using .wide. In SwiftUI, you have two primary approaches to format date objects: the .formatted modifier used previously, and date formatter. While both methods achieve date formatting, they serve different purposes. The .formatted modifier offers a more SwiftUI native, declarative approach, with good performance for simple use cases. However, for more complex formatting requirements, date formatter provides greater control and localization options. Here's how to implement a custom date formatter. The code is a Swift property initialization pattern that creates and configures a date formatter instance using a closure that executes immediately upon property initialization. By using this syntax, we ensure the date formatter is created only once and reused throughout the object's lifecycle, which is more performant than creating new instances repeatedly since date formatter initialization is computationally expensive. The closure sets up the formatter with a specific date format pattern that will display dates in a format like Tuesday, December 17th, 2024. This pattern combines clean code organization, performance optimization, and thread safety, making it a common practice in SwiftUI and iOS development when working with date formatting. To use this formatter in your SwiftUI view, simply call text date formatter string from selected date. The date formatter approach allows you to set additional formatting properties such as locale and time zone, making it particularly useful for applications requiring specific regional settings or complex date representations. For optimal performance, remember to create the formatter as a property rather than initializing it within the view's body. For the next part, we'll customize the appearance of our day view component to create a visually distinct calendar interface. We'll implement different styling for weekdays and weekends to improve visual hierarchy. For weekend cells, we'll apply a unique appearance to distinguish them from regular weekdays. When a user selects a specific day, we'll maintain the background color while changing the text color to white, ensuring optimal contrast for better readability. To help users identify the current day, we'll add a colored border around the cell when it's not selected. Let's walk through the implementation of these visual enhancements using SwiftUI's powerful styling capabilities. Navigate to your day view struct and implement the following calendar-related properties to enhance your date handling functionality. Start by adding the calendar property at the top of your struct. This creates an efficient, reusable calendar instance that will serve as the foundation for our date calculations. By marking it private and using it as a stored property, we optimize performance by avoiding repeated calendar instantiations. Next, implement the IsToday computed property. This property provides a clean way to determine if the view's date matches the current day. Calendar.isDateInToday, date, is a convenient calendar method that compares if a given date falls on the current day. It handles all the complexity of comparing year, month, and day components while ignoring time components. Returns true only if the date matches today's date. Finally, add the isWeekend computed property. This property identifies weekend days by examining the weekday component of our date. In the standard calendar system, 1 represents Sunday and 7 represents Saturday. The condition weekday equals 1 or weekday equals 7 checks if it's either Sunday, 1, or Saturday, 7. Returns true if it's a weekend day, false, otherwise. These properties work together to enable dynamic styling in your day view. IsToday enables highlighting the current day with your teal accent color. IsWeekend allows for distinct styling of weekend dates. With our 3 essential properties configured, we'll implement dynamic text color changes by introducing the text color property. The text color computed property determines the display color of the date text using a priority-based logic system. At the highest priority, if the date is selected, it returns white color to make the selected date stand out. If the date isn't selected but is today, it returns teal color to highlight the current date. Finally, if the date is neither selected nor today, it checks if it's a weekend using a ternary operator, returning the primary text color for weekends and the secondary text color for weekdays. To complete this implementation, update the foreground color modifier by replacing the existing ternary operator with our newly created text color property. This creates a clear visual hierarchy where selected dates are most prominent in white. Today's date is highlighted in teal. Weekend dates are slightly emphasized, and regular weekdays use a more subtle secondary color. To create a more polished user interface, we'll customize the border appearance by introducing a border color property. This property will control the outline of our view. The border color computed property establishes the color of the day view's border using priority-based logic. If the date is selected, it immediately returns the teal color, taking precedence over any other condition. If the date isn't selected, it uses a ternary operator to check if it's today's date, returning teal for today and the default border color for all other dates. We'll then update the stroke modifier to utilize our new border color and implement conditional line width styling, setting it to 2 points, when is today is true, and 1 point otherwise. This creates a visual distinction where both selected dates and today's date are highlighted with a teal border, while all other dates maintain the standard border color, helping users quickly identify important dates in the calendar. For the next implementation, we'll enhance the week view component by adding dynamic navigation capabilities. We'll transform the current static week view into a scrollable interface that allows users to smoothly navigate between weeks using SwiftUI's gesture-based interactions. Users will be able to swipe horizontally to access previous and upcoming weeks, providing a more intuitive date selection experience. Additionally, we'll implement a Today button that instantly returns the view to the current week. Let's break down the implementation steps to create this enhanced date navigation system. Create a new view called Week Row View below the existing Week View component. Next, extract the entire horizontal stack content from Week View into this newly created Week Row View struct. The separation of Week Row View from Week View follows the single responsibility principle and optimizes performance. Week View manages navigation and scrolling, while Week Row View focuses solely on displaying a single week's dates. This separation is particularly important because of how Tab View works. It creates multiple instances as you scroll, and having a separate Week Row View means SwiftUI can efficiently manage memory by loading and unloading only the necessary week views. If we kept everything in Week View, we'd be doing unnecessary calculations for non-visible weeks and making the code harder to maintain. Additionally, separating these components makes debugging easier since issues with week display can be isolated from navigation logic problems. In our Week View implementation, we'll start by declaring essential properties that form the foundation of our scrolling functionality. First, we'll create base date as a constant property of type date. This serves as our anchor point for calculating the entire week's dates, typically starting from the first day of the week. Second, we'll implement a two-way communication channel with our parent view using binding var selected date, date. This binding property is crucial for maintaining state synchronization. When users interact with our week view and select a date, the parent view will automatically receive these updates. The binding property wrapper is a fundamental SwiftUI concept that enables this seamless data flow between views. Third, we'll add a private calendar instance with private letCalendar equals calendar.current. This property accesses the user's system calendar, ensuring our app respects their regional and cultural preferences. Finally, to represent our week's dates, we'll implement a computed property, private var dates for week, date. This property dynamically generates an array containing 7 date objects, one for each day of the week. The implementation leverages Swift's powerful array manipulation features to create the sequence. The property uses a range operation to iterate through the days, 0 through 6, giving us 7 days total. We then use compact map to transform each index into a corresponding date. While compact map typically handles nil values, in our calendar implementation, nil results are highly unlikely since we're performing straightforward date arithmetic. The actual date calculation is performed using the calendar API's date by adding value method, which adds the specified number of days to our base date. Each time this property is accessed, it will recalculate the dates based on the current base date, ensuring our week view always displays the correct sequence of dates. These properties lay the groundwork for building a dynamic and locale-aware week view in SwiftUI. Each one serves a specific purpose in creating an interactive calendar interface that maintains proper state management and user preferences. Let's now focus on implementing the week view component by first collapsing our week row view. We'll start by adding essential properties to structure our weekly calendar interface. State private var week offset equals 0 tracks the current position in the infinite scrolling week view. When it's 0, you're at the current week. Positive values mean you're viewing future weeks, negative values mean past weeks. It changes as you swipe left or right, and can also be reset to 0 when the Today button is tapped. Private let week count equals 301, and private let center index equals 150 work together to create the illusion of infinite scrolling. The total number of weeks shown is 301, week count, with the current week positioned at index 150, center index. This means you can scroll roughly 150 weeks into the past and 150 weeks into the future from the current week. These values are large enough that users won't reach the ends during normal use, creating a seamless infinite scrolling experience without actually being infinite. For example, if week offset is -2, you're viewing the week from 2 weeks ago. If it's 3, you're viewing 3 weeks in the future, all centered around index 150 in the tab view's range of 0 to 300. The dates for week property can now be safely removed from the parent view since we have refactored the H stack and its associated logic into the dedicated week row view component. Next, the current week start computed property is a fundamental component of the calendar system that determines the beginning of the current week, and the force unwrap, ! Is being used on the result of calendar, date, from, which returns an optional date. The force unwrap is considered safe in this specific context because the components being used, .year for week of year and .week of year, are fundamental calendar components that will always exist for any valid date, and we're getting them from the current date. The process works like this. First, date creates a valid current date. Then date components extracts the year and week number from it, which will always succeed. And finally, date from creates a new date from these valid components, which will always succeed. Since this chain of operations cannot fail with these specific calendar components, the force unwrap won't cause a runtime crash. The getDateForWeek function serves as a date calculator that takes an integer offset and returns a date corresponding to that many weeks away from the current week. It uses current week start as its anchor point and employs the calendar's date-by-adding method to move forward or backward in time. The offset parameter can be positive, future weeks, or negative, past weeks, making it versatile for navigating through time. This function is essential for the calendar's navigation system as it enables the view to determine what dates to display when the user scrolls through different weeks. And the force unwrap is safe here because adding a week component to a valid date will always produce another valid date. Finally, the isDateInDisplayedWeek function acts as a date comparison utility that determines whether a specific date falls within a particular week, offset from the current week. It takes two parameters, the date to check and the week offset, then uses the getDateForWeek function to establish a reference point for comparison. The actual comparison is performed using the calendar's isDate method with a .week of year granularity, which ensures that dates are compared at the week level rather than exact matches. This function is crucial for the calendar's highlighting and selection features, as it helps determine which dates should be visually marked as part of the currently displayed week. Now we can start implementing our scrollable week calendar feature in our project. We'll create a horizontally swipeable interface that allows users to navigate through weeks seamlessly. First, locate the on-tap gesture and date picker overlay in your code. Below these elements, we'll implement a tab view component to handle our horizontally scrollable week views. The tab view requires a binding to week offset, which is crucial for maintaining the state of our currently visible week. This implementation creates an intuitive, swipeable interface where users can naturally navigate between weeks. The selection binding parameter ensures that our view remains synchronized with the week offset state variable, allowing for both programmatic control and user-driven navigation through gestures. The scroll view's content is structured around a for-each loop that generates our calendar's weekly views. This creates a scrollable timeline of 300 weeks, with center index set to 150. The timeline extends from -150, past, through 149, future, with 0 representing the current week. Each offset value serves two key purposes. It acts as a unique identifier for SwiftUI through id.self, and it determines the week's position relative to the present. The offset parameter in our for-each loop represents the distance from the current week. When offset is 0, we are showing the current week. Negative offsets represent past weeks, while positive offsets show future weeks. Each week view is uniquely identified by its offset value through the .tag offset modifier. Each week is encapsulated in a VStack that contains a week row view component. The week row view receives two critical pieces of data: base date, calculated using getDateForWeek offset, which determines the starting date of that particular week, and selected date, passed as a binding to maintain state of which day is currently selected. The horizontal padding of 4 adds a small horizontal gap between weeks for better visual separation. Each week view is tagged with its corresponding offset using .tag offset, which is essential for the tab view's selection binding to work correctly. This tag allows the tab view to know which week is currently being displayed and enables proper synchronization with the week offset state variable. This structure ensures that weeks can be scrolled smoothly and that the selected date remains properly synchronized with the visible week, creating a cohesive calendar interface. Tab view style .page index display mode .never configures the tab view to behave like a page view with horizontal swipeable behavior, while hiding the standard page indicator dots that would normally appear at the bottom. The dot frame height 70 sets a fixed height for the week view container, ensuring consistent layout. This implementation creates a high-performance, horizontally scrollable week view component in SwiftUI that provides seamless calendar navigation. Users can effortlessly swipe between weeks using SwiftUI's native gesture handling, with smooth transitions powered by the framework's animation system. To enhance the calendar navigation, we'll implement a Today button functionality. While horizontal scrolling allows users to browse through different weeks, returning to the current date requires manual scrolling. By adding a dedicated button, users can instantly navigate back to the current week and automatically select today's date, regardless of how far they've scrolled in either direction. This UI pattern will significantly improve user experience. To complete the header layout, insert a spacer between the date display, month-year string, with its chevron icon, and our Today button. This will automatically push the button to the right edge. For the Today button implementation, create an H stack with these specific parameters: Create a button containing an H stack that pairs an SF symbol calendar icon, sized at 12 points, with the text Today, using the system's subheadline font. Set their spacing to 4 points. Apply padding of 8 points around this content. For the button's background, implement a Z stack that combines your app container color with a 1-point border in app border color. Style the button's content, both text and icon, with app text primary color and round its corners with a radius of 8 points. This creates a polished, interactive element that matches your app's design system. Let's make our Today button functional by implementing its tap action. Add a closure to the button that resets both the calendar view and selection state. Inside the button's action, wrap the state updates in a with animation block to create a smooth transition. When users navigate to different weeks and tap this button, it will smoothly animate back to the current week while simultaneously updating the selected date to today. The animation wrapper ensures these state changes are visually fluid rather than instant. Let's enhance our button further. The dot opacity modifier dynamically controls the visibility of the Today button using a ternary operator that evaluates whether the current date falls within the displayed week. When is date in displayed week, date, for week offset, returns true, meaning today's date is visible in the current week view. The opacity is set to 0, making the button invisible. When false, today's date is not in the current week, the opacity becomes 1, making the button fully visible. This creates an intuitive user experience where the Today button only appears when users have navigated away from the current week, eliminating redundant UI elements when they're not needed. Learn how to enhance your SwiftUI buttons with dynamic visibility animations. You can implement several eye-catching effects to make your UI more engaging. Scale the button smoothly using dot scale effect. Create a sophisticated fade transition with dot blur. Or combine multiple modifiers for unique custom animations. These animation options give you the flexibility to design interactions that match your app's style and user experience goals. Experiment with different combinations of effects to find the perfect animation that aligns with your design vision. Now, let's improve 2 key aspects of our scrolling component. The first issue involves the month display in the header. While our app correctly shows the current date, December 20th, the month label doesn't update dynamically when scrolling between months. For example, when scrolling from December to January, the header continues to display December until a user explicitly selects a date in January. We need to implement real-time month updates based on the visible date range. The second issue relates to date synchronization between our date picker and week row view. Currently, when a user selects a future date, such as June 30th, 2025, using the date picker, the task list view correctly displays the selected date, but our week row view remains anchored to the current week instead of jumping to the selected week. Let's address the month header update first to establish better date handling throughout our app. Currently, the month-year string computed property formats a hard-coded selected date value, which limits its flexibility and reusability across your SwiftUI view hierarchy. Instead of having the text view directly access this computed property, we can improve the design by making the date formatting logic more modular and reusable. To enhance reusability, we'll transform the month-year string computed property into a function that accepts a date parameter. The new month-year string for function decouples the date formatting logic from any specific date property, making it a versatile utility throughout your SwiftUI app. In your views, you can now pass any date value to this function, such as dynamically calculated dates from getDateForWeek, week offset. In SwiftUI, understanding string handling and text views is crucial for efficient development. Let's explore the key differences between using string interpolation and direct string usage. When you use string interpolation, SwiftUI processes the expression by converting the value into a string type, even if it's already a string. This approach is particularly valuable when you need to combine multiple values or add context to your text. However, when you directly use month-year string in a text view, SwiftUI takes a more straightforward approach. Since text views are designed to work with string values, passing month-year string directly is both cleaner and more performant. While the performance difference is minimal, it's a good practice to write concise, clear code. Here's what you should remember. Choose direct string usage when displaying a single string value. This approach is cleaner and better communicates your intent. Use string interpolation when combining the string with other text or when providing additional context. This refactoring makes text view now becomes more flexible, as it can display formatted dates from various sources rather than being constrained to a single computed property. By centralizing the date formatter configuration and usage in a single function, we create a clean separation of concerns that significantly improves code maintainability. The function's independence from selected date not only enhances its testability, but also makes it more versatile across different view contexts. This dynamic approach allows the text view to adapt and display the correct month and year for any given week offset, providing a more robust and flexible solution for date presentation in your SwiftUI interface. Overall, this refactor makes the code more flexible and maintainable while enabling dynamic date calculations. Next, to ensure proper date synchronization in our calendar, we'll implement date change handling in our week view's main VStack. This critical step connects the user's date selection with the calendar's weekly display. Add the onChange modifier to your week view's root VStack. This modifier is part of SwiftUI's iOS 17 framework and serves two key purposes. It monitors any changes to the selected date property, and it triggers a callback whenever the user selects a new date. The modifier's closure provides two parameters: an underscore representing the previous date value, which we can ignore. New date containing the newly selected date we'll use for calculations. This syntax is optimized to focus only on the new value. Since we only need the new date to calculate the week offset, we can safely ignore the previous value using the underscore. Let start of new date week equals calendar.date from calendar.date components. This line finds the start date of the week containing the newly selected date. It extracts the year and week components from the selected date and creates a new date representing the start of that week. The result is stored in start of new date week. If start of new date week is not equal to get date for week offset. When comparing this start date with our current week position, we use Swift's inequality operator, ! And equal, to detect changes and compares two values and returns true if they are not equal. It's the opposite of equal. For example, 5 is not equal to 3 is true, while 5 is not equal to 5 is false. If the weeks are different, let new offset calculates how many weeks apart the new date is from the current week. Current week start is the reference point, start of the current week. The result tells us how many weeks we need to offset the calendar view. With animation, week offset equals new offset, updates the week offset state with animation. This causes the tab view to smoothly scroll to the correct week. This code ensures that when a user selects a date through the date picker, the week row view automatically scrolls to show the week containing that date, maintaining visual consistency and proper navigation in the calendar interface. To enhance the user experience, we'll implement automatic scrolling to the current time in our task list view. By default, SwiftUI initializes our timeline at 12 a.m., requiring users to manually scroll to find the current time slot. Instead, we'll modify our view to automatically position the current time in the visible area when the app launches. For example, if you open the app at 2 p.m., the timeline will immediately scroll to that time slot, making it instantly visible to users. This optimization, while optional, significantly improves the app's usability by providing immediate context of the current time. Here's how we can achieve it. Now that we've completed our scrolling functionality, you can collapse both the week view and week row view code sections for better organization. Let's enhance the task list view by implementing scroll position tracking. First, add the state property at the top of your task list view struct. State private var initial scroll performed equals false. This state property is crucial for our scroll management system. It acts as a one-time trigger for the initial scroll animation, ensuring optimal user experience. The property serves several key purposes. It prevents unnecessary repeated scrolling when the view refreshes or reappears, ensures the scroll animation occurs exactly once during the initial view presentation, and leverages SwiftUI's state management system to handle view updates efficiently. First, wrap your scroll view with a scroll view reader. Scroll View Reader is a powerful SwiftUI view that enables programmatic scroll control in your calendar interface. This provides access to a scroll proxy object, which acts as your programmatic control center for managing scroll positions. The scroll proxy lets you target specific views that have been marked with unique identifiers. To implement the scroll behavior, add an onAppear modifier to your root scroll view. The system first checks the initial scroll performed flag, which acts as a safeguard against repeated scrolling. When this flag is false, the scrolling sequence begins. The exclamation mark is a logical not operator in Swift and many other programming languages. It inverts a Boolean value, making true become false and false become true. In the context of exclamation mark initial scroll performed, when initial scroll performed is false, exclamation mark initial scroll performed evaluates to true. When initial scroll performed is true, exclamation mark initial scroll performed evaluates to false. So in our timeline code, the check, if exclamation mark initial scroll performed, means if initial scroll performed is false, or in plain English, if we haven't performed the initial scroll yet. This is a common programming pattern for implementing one-time actions. We check if something hasn't happened yet, perform the action, then set a flag to prevent it from happening again. Using calendar.current.component, hour, from date, the code extracts the current hour in 24-hour format. For example, 2:45 p.m. converts to hour 14. The scroll proxy.scroll2 method then smoothly navigates to the corresponding hour view using its unique identifier. Finally, initial scroll performed is set to true, ensuring this automatic positioning only occurs once during the view's lifecycle. Next, in your timeline hour view, assign unique identifiers to each hour slot. Each timeline hour view requires a unique identifier to enable precise scroll targeting. Using the ID modifier, we create a systematic naming pattern for each hourly view component. The identifier follows a consistent format, hour, followed by the hour number, creating a sequence from hour 0 through hour 23 for a full day's timeline. For example, when applying scroll proxy.scroll to hour 14, the scroll view reader efficiently locates the view labeled with hour 14 and positions it according to the specified scroll anchor. This identification system is crucial for the automatic scrolling mechanism, as it creates a direct reference point that SwiftUI can use to locate and navigate to specific positions within your scrollable timeline interface. The systematic nature of these identifiers ensures reliable and predictable scrolling behavior throughout your application. So if you open the app at 2:42 p.m., it will automatically scroll to position the 2 p.m. time slot at the top of the scroll view. This gives users immediate context of their current time position in the calendar. We can also implement an optimized scroll positioning system with a thoughtful time buffer. Our goal is to enhance the user experience by providing better context around the current time. The core of this implementation revolves around a new constant that creates a 2-hour buffer before the current time. We achieve this using Swift's built-in max function with the following code. This expression ensures our scroll position remains within valid bounds, 0 to 23. For instance, when the current time is 3 p.m., current hour equals 15, the view positions itself at 1 p.m., target hour equals 13. During early morning hours, like 1 a.m., current hour equals 1, the view defaults to midnight, target hour equals 0, to maintain a valid scroll position. This implementation significantly improves the calendar view's functionality in several ways. Users gain immediate visibility of their schedule's context, seeing both upcoming events and recent past activities. The current time indicator sits naturally within the viewport rather than at the edge. The interface provides better spatial awareness, helping users quickly orient themselves within their daily timeline. By implementing this buffer system, we create a more polished and professional calendar interface that anticipates user needs and provides a more comprehensive view of their schedule. For the next feature, we'll implement gesture recognition in our custom calendar view component, specifically focusing on the pinch-to-zoom functionality similar to Apple's native calendar app. Let's dive into adding this interactive feature to enhance the user experience of our calendar interface. Let's begin implementing zoom functionality in our calendar by setting up essential state variables. First, we declare two state variables. Time slot scale starts at 1.0 and represents our current zoom level, while last scale, also starting at 1.0, helps us track the ongoing pinch gestures progress. Next, we establish our zoom boundaries. Min scale at 0.5 allows users to compress the view to half its original size, while max scale at 2.0 permits expansion up to double the size. These values can be adjusted based on your specific needs. You could set min scale to 0.25 for a more compressed view, or max scale to 3.0 for greater expansion, depending on your user experience requirements. We set default hour spacing to 40 points, defining our baseline spacing between hour markers. This value can also be customized to match your desired default view density. Finally, we create a computed property called hour spacing, which dynamically calculates the actual spacing by multiplying our default hour spacing by the current time slot scale. This computed property is crucial as it smoothly adjusts our calendar's layout in response to pinch gestures, ensuring that when users zoom in or out, the spacing between hours grows or shrinks proportionally while maintaining a natural feel. In our next step, we modify the timeline view to support dynamic spacing. Previously, our timeline had a fixed spacing between hour markers. Now, we introduce a new parameter called hour spacing of type CG_float. This parameter will be passed into the timeline view from its parent. Inside the v-stack of our timeline view, we replace the static spacing value of 40 with our new hour spacing parameter. This change means that when users perform pinch gestures, the space between each hour marker will expand or contract smoothly. The v-stack's spacing parameter now uses hour spacing instead of a hard-coded value, allowing the entire timeline to respond to zoom gestures while maintaining proper proportions between all elements. Moving on to the current time indicator, we make similar adjustments to ensure it stays synchronized with our timeline's zoom level. A key change here is the modification of the hour spacing property. We remove the private and hard-coded value by changing it from private let hour spacing, CG_float 40, to simply let hour spacing, CG_float. This transforms it from a private constant with a fixed value to a parameter that can be passed in. This modification is crucial because the current time indicator needs to calculate its vertical position based on the current time. In the indicator offset calculation, we now use this dynamic hour spacing instead of the previous fixed value of 40. This ensures that as users zoom in or out, the current time indicator maintains its correct relative position on the timeline, moving smoothly with the rest of the interface and staying perfectly aligned with the hour markers. Now that we've modified both timeline view and current time indicator to accept hour spacing parameters, we need to update how we call these components in our task list view. We find our previous implementation, where timeline view and current time indicator were called without any parameters, which would now cause compilation errors since they require hour spacing. To fix this, we locate these component calls within the h-stack and update them to pass our dynamically calculated hour spacing value. For timeline view, we add the parameter hour spacing, where the first hour spacing is the parameter name and the second refers to our computed property. Similarly, for current time indicator, we add the same parameter hour spacing. This ensures both components receive the same spacing value, maintaining visual consistency as users zoom in and out. The timeline and current time indicator will now scale together smoothly, as they're both using the same hour spacing value derived from our zoom calculations. Now we'll add pinch to zoom functionality to our calendar view. We attach a gesture modifier to our main v-stack of our view using .gesture and implement magnification gesture to handle pinch gestures. When the user pinches, onChanged is called continuously with the current scale value. First, we calculate delta by dividing the current value by last scale. This tells us how much the pinch has changed since the last update. We then store the current value in last scale for the next calculation. Using this delta, we compute our new scale by multiplying our current time slot scale by the delta, which gives us smooth, incremental scaling. To keep our zoom level within reasonable bounds, we use min and max functions to clamp the new scale between our predefined min scale of 0.5 and max scale of 2.0. Finally, in on ended, which is called when the user finishes the pinch gesture, we reset last scale to 1.0, preparing for the next pinch gesture. This implementation ensures smooth, controlled zooming that feels natural and maintains the view's usability. We can enhance the gesture by adding an animation to create a more fluid and polished zooming experience. We apply an animation modifier that uses interactive spring, which provides a physics-based animation that responds naturally to user input. The response time of 0.3 seconds keeps the animation quick and responsive, while not feeling abrupt. The damping fraction of 0.7 adds just enough bounce to feel natural, not too springy, but not too rigid either. We set the blend duration to 0.1 seconds, which helps smooth out any rapid changes in scale during pinch gestures. This animation is tied specifically to changes in our time slot scale value, meaning it will only trigger when the zoom level changes. As users pinch to zoom, the animation creates a smooth transition between different scale values, making the calendar's resizing feel more refined and intentional, while maintaining the responsiveness needed for precise control. In our final implementation step, we modify the task container's layout to respond to our zoom gestures. We update our VStack that contains the calendar tasks to use dynamic spacing by replacing the fixed spacing value with our computed hour spacing property. This modification is crucial because it ensures that the tasks maintain proper vertical positioning and spacing relative to our timeline when users zoom in or out. By using hour spacing in the VStack's spacing parameter, tasks will spread apart or come closer together in perfect synchronization with the timeline markers and current time indicator, maintaining a cohesive visual relationship across all calendar elements. As a finishing touch, we wrap our scroll view content with a geometry reader. While our calendar appears to function without it, the geometry reader serves a vital purpose in creating a polished user experience. By capturing the available space with geometry reader and using geometry size height to set a minimum frame height, we ensure our scrollable area always fills the screen, even when there are few events. This prevents the awkward behavior where the scroll area might shrink on days with minimal content. When zooming, this consistent container size becomes particularly important as it provides a stable foundation for our pinch gestures, preventing any unexpected layout shifts that could disrupt the zooming experience. Now that our pinch to zoom gesture is complete, we can enhance the user experience by adding convenient tap gestures for quick zoom controls. Using simultaneous gesture, we first create a double tap handler with tap gesture count 2. When the gesture ends, we use with animation to wrap our scale changes in a spring animation. The animation parameters, response, 0.3 and damping fraction, 0.7, create a smooth and natural zooming effect. Inside the animation block, we set time slot scale to 3.0, though this value can be adjusted based on preference, and reset last scale to 1.0 to maintain consistency with our pinch gesture state. This double tap implementation gives users a quick way to get a detailed view of their schedule. Important note about zoom values. While we've set a max scale limit of 2.0 for pinch to zoom gestures, the double tap zoom value can be set independently. If we change the double tap zoom to 6.0, for example, users could zoom in much further with a double tap than they could with pinching. This could create an inconsistent user experience, so choose the double tap zoom value carefully to maintain harmony with the pinch to zoom limits. To complement the double tap zoom in, we'll add a single tap gesture to reset the view. However, we want this reset to be smart. It should only trigger if the view is currently zoomed in or out, when time slot scale isn't 1.0. When users single tap and the condition is met, the view smoothly animates back to its original scale using the same spring animation parameters. This creates a smooth transitions between zoomed and normal views. Both gestures reset last scale to 1.0 to ensure consistent behavior when switching between pinch and tap gestures. These tap gestures work simultaneously with our existing pinch gesture, giving users multiple intuitive ways to control their calendar view. The combination of pinch to zoom for precise control and tap gestures for quick actions creates a more versatile and user-friendly interface. Starting from a basic Figma design mockup, we've transformed a simple daily view into a feature-rich calendar implementation in SwiftUI. One of our key enhancements is this multi-level calendar system, which allows users to seamlessly navigate between different timescales. If you're interested in expanding your calendar's functionality beyond the basic daily view, visit our website to access the complete tutorial series.